Right, so now we'll move on to the tutorial number 9 and looking at shear stresses and looking at that tutorial exercise that I spoke about in the lecture notes. And if you turn back to your lecture notes and have a look at them on page 21, you'll see that the span of the beam was 4 meters, the breadth was 300 millimeters, the effective depth 600, the overall depth is 670, allowable concrete cylinder crushing strength 32 MPa, exposure was A2, the dead load excluding the beam was 80 kilonewtons per meter, and the live load 105 kilonewtons per meter. So what I've done, and you've probably seen this by now, I sort of divide the page up into 2 in some cases and get straight on to working out what the total factored loads are. The self-weight of the beam is 0.3, the breadth of the beam in meters, 0.67 the overall depth of the beam, and the mass of concrete is 24 kilonewtons per cubic meter. So if you do the arithmetic, you'll find that your beam weighs 4.82 kilonewtons per meter. So your total dead load then is the 80 that's been given to you up here, plus the self-weight of the beam, 4.82, which gives you a total self-weight of beam of 84.82 kilonewtons per meter. We now factor the loads in terms of limit state. We've got 84.82 being the dead load by 1.2, plus the live load of 105 kilonewtons by 1.5, which gives us the total load per meter along the 4 meter beam of 259.28 kilonewtons per meter. You don't have to take moments to find the reactions, because if you take the total load in the beam and divide it by 2, due to symmetry, RA will equal RB. So what I've done is I've taken the load per meter multiplied by 4 meters, divided it by half, multiplied it by half, or divided it by 2. So each reaction, 518.56 kilonewtons. That also happens to be the shear force on either end of the beam, 518.56 kilonewtons per meter. Sorry, not there. Now, by coincidence, the moment in this particular case, the load per meter multiplied by the span squared divided by 8, the old WL squared over 8 equation, gives you a maximum bending moment of 518.56 kilonewton meters, a standard parabolic bending moment for a beam with a uniformly distributed load. This is your shear force diagram where you have a uniformly distributed load. You've done this many times. So I think that's all pretty clear. We can move on then and calculate what tensile area of steel we need. Lambda from your graph here, lambda, this is what we're looking for there. We're looking for a factor along the bottom axis, equals your ultimate moment divided by the breadth times the effective depth squared. Doing that arithmetic gives you a factor of 4.8. We find a lambda of 4.8, and looking at the graph then, going along to 4.8, going up to 32 MPa, we go across and find that our steel factor P is 0.013. There we have it. Area of steel is PBD, which is the factor for the reinforcing steel times the breadth times the effective depth. We need 2,340 square millimeters of steel. Just fortunately in this particular case, 3 N32 bars give us 2,400 square millimeters, which is very, very close to the required amount. It's only 60 square millimeters difference. Always erring on the high side, guys. Please remember that. Now we need to take cognizance of the beam width. So the beam width required to house 3 N32s is 228 millimeters. And I'll just recap on that, just to refresh your memories. Let me find the right document. If we choose 3 N32s, you could see there we need a beam width of 228. If we'd gone for 4 N28s, which is 2480, which would have done the job as well, we needed a beam width of 326, and there's no way we could have fitted those 4 N28s into the beam. So what I've done, I've chosen 3 N32s, and we comfortably get the 3 bars into the bottom of the beam with room to spare, which makes the vibration of concrete and the placing of concrete a lot better as well, where you don't have too much congestion with reinforcing steel. So moving on, we are going to check the shear now. And I've referenced it back to your lecture notes, which we went through a bit earlier. First thing we have to do, just to go over it again, the first thing we do is we work out the maximum permissible shear force that you can put on that size of concrete section, that size of concrete beam. That's this first calculation. The second calculation, B, is the capacity of the beam with taking into account the tension or the bottom steel only, no ligatures. And the third calc that we do, C, takes the standard spacing of ligatures as prescribed by the code, and we check what the capacity is there, because in some cases it might be adequate actually, and you won't need to work out any more shear steel. In this case it isn't. And the fourth point, D, we work out the spacing of N12 legs for the maximum shear force of 518.56 kilonewtons. So going back here, we work out the maximum permissible shear force. The shear depth, or effective depth as we've been calling it, is 600 millimeters, and that's been given to us. The maximum, the VU max, that concrete section can take with no steel is a standard factor of 0.2 times the cylinder strength of the concrete times the breadth of the beam times the effective depth in newtons, and if we multiply it by 10 to the minus 3 we get into kilonewtons. So you can see that it can comfortably take a total shear force of up to 1152 kilonewtons, which is greater than the shear force that we've computed for this problem of 518.56 kilonewtons. So it is okay. The beam size is okay. You have to confirm that. Now, the shear capacity, taking the tension or bottom steel into account as well, is worked out as I did previously in the lecture notes there. PV, the area of steel over BVDO. The area of steel we have 2,400 square millimeters, multiplied by the breadth of the beam times the effective depth. It gives us a factor of 0.01. Now, if I just get the graph out, the two graphs, if you just bear with me while I get those out. Looking at graph V1, where we V1C, we check out what PV is, and that is the ratio at the bottom, 0.01, there it is, there the axis of that is, and we're looking at 32 MPa. We're looking at 32 MPa, so we're going to up to 0.01, and we go across to the left, and we get a figure of 0.48 for V1C, because that's what we're seeking, V1C. Then, using the standard formula to find the actual factored strength of the concrete, 5 VUC, we've got the 0.48, which we've just looked up on the graph, multiplied by the breadth, the depth, 10 to the minus 3 to bring it to kilonewtons, and we get a strength with tension steel only of that beam of 86.4 kilonewtons. Okay, so just to recap, first step, we found out what the maximum shear force is that you could put on the beam. Second step, we found out how strong the beam was with just the tension reinforcement. And the third part of the question asks you to work out what strength you would get out in shear where you used the standard lig spacing as per AS 3600. And this, as I said previously, I've said it a couple of times, the lig spacing is the lesser or the least of 0.5 times the overall depth, or 300. Now our overall depth is 670 millimeters, so half of that would be 335, which is clearly more than the 300 stipulated by the code, so we use 300 millimeters. And we can now work out what the shear capacity is with N12 ligs at 300 centers. Using this formula, we've got 5 VUC, which is the shear capacity with the tension steel, because the tension steel is still in the beam. So we add that to this calculation we're going to do there to get the total strength of the beam with standard spacings of ligatures, with taking into account the tension steel. So there the tension steel is 86.4. Phi is a standard which you'll find earlier in one of the earlier tables in this series of lectures for shear. 0.6 multiplied is also a standard factor, multiplied by the breadth of the section times the effective depth, and again 10 to the minus 3 to get into kilonewtons. So the strength with standard ligatures at 300 centers and your tension reinforcement is 162 kilonewtons, which is well short of the actual shear force that you have in there of 518.56 kilonewtons. So I've written okay, but it would work, and it will work on part of the beam, as I'll illustrate shortly. The next thing we do is we work the D, as we did in the lecture. We work out the spacing of N12 ligs for the maximum shear force of 518.56 kilonewtons. So what we're looking for is the amount of shear that we have to cater for by using closer spaced N12 ligs. We subtract the strength of the beam, shear strength of the beam, encapsulating just the tension reinforcement, because what we've got to work out in this calculation is what spacings we have to put the ligatures in to carry this residual load of 432 kilonewtons. That is there anyway, thanks to the tension reinforcement. This is the total shear force. This is the force that has to be carried by your N12 ligatures at whatever centers they are going to be, and they're going to be a lot closer than 300 millimeters, I might tell you. So we work out 5 VUS over DO, which gives us a figure of their 5 VUSs there, divided by DO, gives us a figure of 720 millimeters from chart number 2. Not 720 millimeters, just a ratio of 720. So 5 VUS is 720, you go up to 720, come across to your N12s, come down the graph to the bottom axis, and you'll find that it's close enough to 110 millimeter centers. So what we have to have where our shear force is right up in the 518.56 kilonewtons is we need ligatures at 110 centers. And when I detailed this, I actually showed that, and I'll come back to this, but there it is there. I've got the ligatures where we don't have a shear problem at 300 centers, where we have a shear problem at 110. Now I just want to illustrate what I've done. This there is a 4-meter beam. We're only dealing with half of it because it's symmetrical. Whatever we do to this half is going to be reflected, mirrored on that side. We've got a maximum shear force of 518.56 kilonewtons there, diminishing down to nothing at the center. That's if you've drawn just the shear force diagram, there the line is. This green block denotes the resistance offered by N12 ligs at 110 centers. Now it just does the job at the support, but it's doing far more than that at this point. And the reason that I've done this particular problem this way, and there are manifold ways of doing these problems. I mean, you could be changing the centers as you went along as the shear stress increased, but I've just simplified this by having two lots of spacings. We've got the N12s at 110 there. In the centerpiece there, where the shear strength at using just normal ligatures at 300 centers allows you to equal the actual shear force, we can actually put those right across in the central part of the beam in 12 ligs at 300 centers. So all I've done is do this. It's quite a useful sort of way of illustrating things. And I've said the shear resistance supplied by N12 ligs at 110 centers, see D above, that's what this is, from there to there. It satisfies the requirements. This shear resistance here is satisfied by the N12 ligs at 300 centers. See calculation C. So it's pretty straightforward, because when you look at that diagram in conjunction with the beam, you can see what I've done. There your N12 ligs are at 300 centers. I always put them about 100 millimeters away or so from the face of the column, though as the code says you can go even up to the effective depth away. I always play it a bit safe, come maybe 100, 150 away from the face of the column to start them. Got your N12 ligs at 110 centers to that point there, and then we've got N12 ligs at 300 centers across the central part of the beam there. So that's pretty straightforward. And I think I've made a beautiful job of the drawing, don't you guys? I can't hear anybody clapping, but we'll have to live with that. So this is a cross-section through the beam, showing your N12 ligs at 110 centers, 3 N32s in the bottom, 2 N12s in the top. There they are, 2 N12 tie bars. Those bars are there merely to tie the cage together so it can be fabricated or prefabricated. And that's the score. I hope that you have been suitably enlightened. But you can always send me an email, as I've said to you in Connect. Only one email per student per week, but you can put all your questions on there and I will answer them at my earliest convenience. Thank you very much.